So our group did number theoretic algorithms, and number theory is an interesting field because for a long time it was not seen as that useful because it doesn't have um, a lot of really obvious applications like say geometry or calculus do, which have really obvious applications when you first work with them. It's really obvious what you can use them for. But number theory is the study of natural numbers, and we look at things like primes and Fibonacci numbers and things that just aren't generally as useful at first glance. But as computers became really prevalent, um, number theory applications became much more useful, especially in areas like security. And there's other areas too that it's useful for, but it's mostly useful for security.
All right, so I'll be going over the problem statement. So Euclid's algorithm is actually the fastest way to find greatest common divisor of two numbers. There are actually multiple applications for this. One of the most prevalent is actually encryption. So we can actually explain later on how the extended algorithm as well as the normal algorithm can find that. So you can see that if, say, for instance, we have we have two numbers x and y, and we want to find the divisors between those two, we can use a and b. And so we could say ax plus by equals d. And so a and b have to be non-negative numbers. So that would also mean that the two numbers that you are trying to find the GCD for would also have to be non-negative.
As previously stated above by one of my group members in the application section, a Euclid's algorithm only has a few mathematical applications. This made it very difficult for me to find some good recent work involving Euclid's algorithm. However, I stumbled across somebody trying to use a Euclid's algorithm to solve diaphatine equations with only one parameter. To keep this short, a diaphatine equation is basically a linear equation that has a lot of solutions. So now using Euclid's algorithm, we would say our one parameter would be that the solution given back to us, the numbers must be prime. Now taking this even a step further, we could use those prime numbers from the already encrypted solution as keys for RSA encryption. Now this would make the keys for RSA encryption, which are already encrypted, even more encrypted, which is kind of crazy. So we would take our prime keys, which the numbers have to be prime, which makes it perfect to use Euclid's algorithm because you can pass it one parameter. And then we would encrypt the solution basically to the equation, so the only way we could get back to the numbers that we had was solving the equation again using Euclid's algorithm, which people really wouldn't know. So I guess this is just kind of a sneaky way to get our prime keys using Euclid's algorithm for RSA encryption.
All right, so I'm going to be going over elliptic curve cryptography as well. So as I mentioned before, the Euclid's algorithm can be used for this specifically. With the authors of this paper actually used the extended method, and RSA uses it a little bit, but the fact with RSA is that Google has created a quantum computer so they can determine what those prime numbers are that creates the RSA encryption. But it's more on its way out. Elliptic curve cryptography, although, is actually more secure, and it's actually, I think it's more secure personally, but I know this isn't really a thing of debate, but that's more my opinion. A little bit harder to crack, as well as for those of you that attended Jeremy's talk back in October, I think it was, he actually talked about another method in like the 10,000th dimension, which was actually very interesting, using, it was like I can't remember exactly what it was, but it was really interesting. For those of you going over the cryptography course next semester, he will be covering that. Most likely he will also be covering this as well, the elliptic curve. The elliptic curve actually uses a modified version of the algorithm, but of the extended algorithm, but it's not terribly different from what I could tell. But yeah, so as I stated before, you can see through here that it actually uses the Euclid's algorithm with cryptography, and it's actually an improvement on RSA because it actually has a shorter key length. So, yeah.
Now I'm going to talk about the idea of Euclidean rhythms, which are laid out in this really interesting paper by Gottfried Toussaint. And so basically the idea of a Euclidean rhythm is some rhythm with B total pulses, which you could think of it as like pulses in a measure, and then A of those are active pulses. And so we have the rule that B has to be greater than A. It could be equal to, I guess, but really greater than, because that's how you're going to have interesting rhythms. And so, for example, the Euclidean rhythm E38 is going to be defined right here. And so what this is it is the most even distribution of those 3 active pulses over the 8 total pulses. And this particular Euclidean rhythm is known in Brazilian music as a tresillo. And it's really an interesting paper by Gottfried Toussaint. He goes through and he defines all different classes of Euclidean rhythms. The really interesting one that sticks in my mind is the class of Euclidean rhythms where both A and B are prime. And they end up being a very interesting class of rhythms. And he also classifies the Euclidean rhythms by where they are most common, like in different types or different parts of the world, different types of music, which was really interesting. I really recommend anybody reading that paper who wants to. And so this whole application is based upon using the Euclidean rhythm to find a pattern that has the most even possible distribution that you can have. And this idea of finding patterns with an even distribution is also useful in a bunch of other areas of study that I list them all out down here. I think the most interesting ones are generating linear graphics and calculating leap years in calendar design. I think those are both just really interesting applications that you maybe really wouldn't think that you could use the Euclidean algorithm for, but you can, and that's pretty cool. Okay, so now I'll talk about the algorithm solution for the regular Euclid's algorithm. And so here's the pseudocode for it right here. It's pretty simple. All it's going to do is it takes 2 parameters, A and B, and if B is equal to 0, return A, and otherwise it will return a recursive call to itself with the parameters B and A mod B. And so just to go through this, the algorithm really relies on this fact right here that greatest common divisor of A and B is equal to the greatest common divisor of B and A mod B. And I'm just not going to prove that right now because we don't have the time, but if people have questions about that, I'll be happy to answer them. And then the algorithm recursively calls Euclid B A mod B unless B is equal to 0, which as we discussed in the pseudocode. And we know that we'll always get down to some case where B is 0 since A mod B is less than B. So you'll keep making calls like that until you eventually will have to get down to 0. And then if B is equal to 0, we know how to calculate this greatest common divisor of some number X and B, since the greatest common divisor of X and 0 will always be X, since the greatest divisor of any number X will be that number X, and then every number divides 0. So it follows pretty quickly. The greatest common divisor of X and 0 will always be X. So then, since like I said, we'll always get down to some case where we're like this because of how the recursion works. We'll end up with a recursion chain that looks something like this, where you have your original call to Euclid AB, or the greatest common divisor of A and B, is equal to this call, this first recursive call, with B and A mod B, and then you'll just keep chaining that down until you get down to somewhere that looks like this. And because of this statement up here, all of these are going to be equal. So then, since we know how to solve this, and it's equal to this up here, we know how to solve this. Okay, so now I'm going to really quickly go through the solution for the extended algorithm. And so right here is the pseudocode. And right now I'm just going to talk about the first case, which is basically the same as in the regular algorithm, that it's going to return A if B is equal to 0, but then it's also going to return these X and Y values of 0 and 1. And that's because we're returning A as our D value. So that means A times 1 plus B times 0 is always going to be D. So that's pretty obvious. I think that termination case is good. And then this one is a little bit more complicated. I'm going to pop over here. And so this one, as we said, we'll enter on line 5, and we'll calculate D prime to be the greatest common divisor of B and A mod B. And because of this, we can state that this next statement is true, that D prime equals A X prime plus A mod B Y prime. And that's just a common trait that greatest common divisors have, that you can write these as a linear combination. So then that gives us that all of these things are true, but we want to know that this here is true, that D equals AX plus BY. And we can get that by rewriting this equation here, the D prime equals B X prime plus A mod B Y prime, using some theorem 3.8, which I'm just not going to go over for time's sake. But no, you get it back in this form. So then we know if we choose X to be Y prime and Y to be X prime minus BA over BC times Y prime, which is what we do on line 5, then we'll get this linear combination. That is what we wanted. Okay, so then for the example of the regular Euclids, we're going to use this example input of 48 and 36 as our parameters A and B. And so on the first line, we'll call Euclid 48, 36, and that will enter the else on line 4 because 36 is not equal to 0. So then we'll make this call Euclid 36, 48 mod 36, which is equal to this call here, GCD 3612. So then we make that Euclid call, and that again, 12 is not 0. So we'll do this call to Euclid again with 12 and 36 mod 12, and then we'll do the same thing. That comes down to this greatest common divisor of 12 and 0. We'll do that call, and we'll finally get down to the termination condition because B equals 0 right here. Oops. Right here. So then we will get the greatest common divisor of them is 12. And again, you'll get this kind of chain like this, where you get the greatest common divisors are equal to each other down the chain until you can calculate what they are.
What's up, guys? I'm going to be doing a walkthrough of the Euclid's extended algorithm. So we're going to try to find integer coefficients for our two inputs, and our A value is 48 and our B value is 36. And this is the same as the normal Euclid's algorithm. So our B value becomes 36, and I wrote this out just to save time. Our B value becomes 36, and then 36 goes into 48 with a remainder of 12, so that's our new B value. And then our B value becomes our A value, so 12, and then 12 goes into 36 with no remainder of 0. So our algorithm would return, and our greatest common divisor is 12, so we can write that all the way up our chart. And then we return 1 and 0 for these values. And then I'm just going to calculate the floor of A over B. So this is 1, this is 3, and 12 over 0 is divided by 0. So now we need to find our new X and Y values all the way up. So our x value, our new x value is going to be our old y value, so this is 0. And then our new y value is our old x, so 1 minus our floor, which is 12, times our old y value, which is 0. So 12 times 0 is 0, 1 minus 0 is 1, so this new value is 1. And then we go up another level, so our new x value is our old y value of 1, and then our new y value is our old x, so 0 minus, and then our floor, which is 1, times our old y value, which is 1. So we get 0 minus 1, which is negative 1. So our two integer coefficients are x and y, and so we can solve our greatest common divisor. So 12 is our greatest common divisor, and that should equal our a value, which is 48 times 1, plus our b value, which is 36, times negative 1. If you calculate that out, 48 minus 36 is 12, and our two integer coefficients for a and b are 1 and negative 1.